So, dear friends, students, in this video I'll be talking about resonance scattering. This is the fourth unit of our syllabi, quantum mechanics second. And, and to start with, I think it would be right if we take on our basic equation of quantum formalism, and that's Schrodinger's equation for scattering. So if I consider that I have a particle and this particle has energy E, and and this particle is incident on some potential, say V of x in one dimension, I can write down the time independent Schrodinger's wave equation. And what's that? That's minus h cross square by 2m, then d2 psi of x by dx2 plus v of x, and psi of x equals e psi of x. So this is our Schrodinger's time independent equation, and for this v of x, what it does basically, this v of x represents localized potential, localized potential. And this localized potential can be, if we take an example of this localized potential, we can think in terms of a scared well, or some kind of barrier. And for this, we can think in terms of the solution. We have incoming wave, and we have incoming wave, and if I call that as psi in of x, that's going to be e to the power of I kx. And then we will have the reflected wave, and we will have a transmitted wave. So we will have a reflected wave, and here I have psi reflected along x is e to the power of minus I kx. And then I will have transmitted wave, and that is psi t of x is e, it is t, the thickness, e to the power of I kx, where this what we call as here I should have, for for reflection I would use a constant here, say I will use r, and for transmission I will use t as a constant. So this r and t, they are reflection and transmission coefficients. R and t, they are reflection and transmission coefficients. Okay, so what's our target? Our target is resonance, and we understand resonance in classical domain. If we rightly go back to our class 12 physics, we have the classical resonance, and that resonance is basically defined in terms of the incident energy and the energy of oscillation. Now if we have an oscillator, a classical oscillator, and it's oscillating with some frequency, say nu, and if we have something else, maybe some disturbance, and this disturbance has also the frequency in the range of this nu, if the two frequencies match, the amplitude of the resultant wave is maximum. But here we are discussing the things in the domain of quantum world, and k, as we know, k is I can take this k as 2m e by h bar. Now, in case of resonance, uh, the wave function. Now we are talking about the quantum mechanical uh, action. So the wave function that we have inside the potential. So if I assume for the time being that we have a potential and we will have a wave function inside this potential, okay, and what does this wave function behave within the potential? This wave function is assumed to behave like a standing wave, like a standing wave. And this is what basically corresponds to the quasi bound state, because we are trying to do things within quasi classical limits. So this trapped wave function will form a bound. It will behave like a standing wave. So now the wave function for the resonance, if I take on psi Re, Re will be my resonance. That will be Ae to the power of Ik resonance, then X plus Be to the power of minus Ik resonance X. So what this KRE that I have introduced here, it is basically related to, to resonant energy. Resonant energy. So if I take that resonant energy as E of R, so now the boundary condition at the edges of the potential, you will have the boundary conditions. You understand those problems in the basic problems in quantum mechanics, and at the edges of the potential, what they do is they calculate these coefficients, the coefficient A and the coefficient B. So these coefficients can be calculated, and the calculation of these coefficients and that's what leads to what's called as phase shift of our outgoing wave. Now another important thing in the same context is the width now. Okay, so now the wave we have in this forbidden region and the lifetime of this resonant state, if I assume that lifetime of resonant state, if I assume that is tau, this tau is related to the time it takes for this quasi bound state. So this is my quasi bound state. This is my quasi bound state. So this time, the lifetime of resonant state, is basically related to the time it takes for this quasi-bound state to decay. And the decay rate, that's T, is related to the resonance width. So this is my resonance width. So there is a relation between tau and the half T. All right, and what is this? This is the resonant. This is the resonant width. This is the resonance width. All right. So and these things can be found by solving the time-dependent Schrodinger's wave equation. I mean the lifetime of the resonant state and the resonance width. Now these things can be evaluated using time-dependent Schrodinger's wave equation. So to move on from here, now in order to derive that relation between the resonance width, what's the resonance width? That's this half t, and uh, and the decay from the perspective of the quasi-bound state, we will approach this problem using time-dependent picture or time-dependent Schrödinger's equation. So what we do here is we start by considering a resonant state that's temporarily trapped within the potential. So we assume that we have a resonant state, and this state is trapped within a potential well, and eventually it decays and giving rise to some exponential decay law. Now, if I write down my time-dependent Schrödinger's equation, if we recall that, what is that? That's I h bar dou by dou t of psi x and t is equal to h psi x and t. All right, and we understand the meaning of the symbols. This H is our Hamiltonian, and it's the Hamiltonian of our system. And in the context of resonance scattering, this H typically represents a potential well. It represents a potential well, or you can also say a barrier that can trap a wave, that can trap a particle or a wave for some finite time. That is the representation of this Hamiltonian. Now, what happens in resonance scattering? The particle is momentarily trapped in the quasi-bound state. And what happens then? Then there is a decay, which decays after some time. And the wave function of this quasi-bound state, the wave function of quasi-bound state, if I write down that as psi of xt is psi, I should introduce here res, psi resonance of x e to the power of minus e t by h bar. Okay, so that's it. So this is my wave function for this quasi-bound state, which I have tried to write in its simplest form, where the point is, which energy is this now here? Now this E it's a complex energy. You have a quasi-bound state. You have a wave function trapped in a potential well, and its energy is going to be complex. So this E that's over here, this E is complex energy. It's complex energy of this quasi-bound state that I have been talking about. And essentially, for a resonant state, the energy E that we have is not purely real, but it has small imaginary part that reflects that basically reflects the decay of that state, because this state has to decay. But if it has to decay, that decay can be reflected by the imaginary part of this energy. And what we have that, so this E, which is a complex energy, is assumed to be made of ER minus I, this resonance width divided by 2. Where this ER is what? This ER is the real part of the energy. Is the real part of energy. And what does it represent? It represents the resonant energy. It represents the resonance energy, you can say. It represents the resonance energy. And this part, this half t part, what is it? It's the width. It's the width of the resonance related to, it's related to what I already defined. It's related to the lifetime, of state. So we have a complex energy, and this complex energy is made of two parts: real part of energy, which is called as resonance energy, and the imaginary part of energy, which is linked with the width of the resonance. And this width of resonance is related to the life of that state. So if I substitute this complex energy into the wave function, so we have the wave function. Where is that? This is my wave function. And for this E, I will use this complex energy. So how will my wave function look like? It will look like psi of xt equals psi resonance e to the power of minus I times er minus I half t. This is the resonance width, divide by 2 times t. All right, so I can write this as, see, the beauty of this wave function, psi resonance is e to the power of minus I er, it must have divide by h bar, divide by h bar, oh sorry, it has to be here, h bar times e to the power of minus I, this I and I will make you iota square. Iota square is minus 1 and minus minus is plus. So finally you will have minus here. So this is e to the power of minus resonance width times t divide by h bar. Okay, this is my wave function for this quasi-bound state. So what's the beauty of this equation is, the beauty is that this part is the oscillatory part. I should quote down this. I mean, e to the power of minus I er by h bar, it is oscillatory part, corresponding to the oscillations with energy er. And the other part, that is e to the power of minus resonance width times t by h bar, this is the decay part. So things are happening very fast. And what does it represent? It represents the exponential decay. This is representing exponential decay of the amplitude over that short time. So what can we say here is, I can say that the probability amplitude decays exponentially with the characteristic time scale that's governed by this resonance width. This is how the decay part is playing its role. Now, if I have to write down the total probability for finding the particle in this quasi-bound state, what should I do for that? I would like to take the square of the mod of square of this equation, right? And in that case, what am I going to do is, so I think it's preferable to write down total probability of finding the particle in quasi-bound state, and that should be basically the mod of square of my wave function. And what will be that? That will be psi resonance of x whole square and e to the power of minus uh, resonance width and T by h bar. The other part is going to cancel out because you have to take the complex conjugate. When you take the complex conjugate, the oscillatory part is going to boil down to 1, and what we will be left with is the resonance width here. Okay, so the probability is, again, what's happening to the probability now, it decays exponentially, and the decay rate is given by this, what we call as resonance width. Now, to relate this resonant state that we have, we note that the lifetime is the time it takes for the probability to basically decrease by a factor by 1 by e. So in that case, what will be my exponential function? E to the power of minus resonance width t by h bar is equal to e to the power of minus 1. So when I take this t is equal to, say, some tau, and I have to define this tau now. So we can see from here this this resonance width, and t I will replace by tau by h bar is equal to 1. Okay, so we have this tau equal to h bar by resonance width. Now this tau is what? This tau is our lifetime. It's the lifetime of this quasi-bound state. And this tau is the characteristic lifetime of what? It's the characteristic lifetime of resonance. So resonance will take place for this amount of time. And see the beauty of this equation, that it's simply the ratio of the reduced Planck's constant and the width of this what we call as, and the width of resonance. Now, to summarize this lecture, what we have done basically is we have calculated the quantity tau, and this is not tau. This is called resonance width of the resonance, because it determines the range of energies around ER, and ER is what? It is the resonance energy, and this resonance width is small, and if this resonance width is small, then what does that mean from this equation point of view? It implies long-lived state, and long-lived state means sharp resonance. While if we have large resonance width, and what it corresponds to the short lived state, and this is my broad resonance. And I think this can be purely evaluated. I mean, for this resonance width to be small, it will lead us to what I call as sharp resonance, because tau is h bar by resonance width. Okay, and for large resonance width, we will have broad resonance. Okay, and in scattering theory, what we have is the resonance width can be determined. It can be determined from scattering amplitude as well, and which describes the relationship between the incoming and the outgoing waves during the scattering. Now, what happens near the resonance? Near the resonance it's better to move a little bit further to write down things in terms of the scattering amplitude. And if I do that, what we do is near the resonance, we have this f of k. If I define it in terms of k as scattering amplitude, this f of k is resonance width divided by 2 divided by ER minus E, then minus I T by 2. If you go back to the classical physics of 12th class, you have the similar kind of equation, even though there are roots and all that. But it somehow it has a resemblance with resonance amplitude. So here, what we have the width, and this width appears explicitly in this expression. And what does it mean? Reflecting how the resonance affects the scattering process. So how the resonance width affects the scattering process. So this is my scattering amplitude in terms of resonance width and resonance energy, total energy, and the contribution from the contribution from this is my, again, resonance width. And this is basically called as this equation is called as Bright-Wigner distribution. And oh no, no, this is my scattering amplitude. I'm at scattering amplitude. This will come, I'm sorry, this will come when I will calculate the scattering cross section. I mean, when I will calculate scattering cross section in the domain of this resonance that we have been discussing. So finally, that's what we will obtain as Bright-Wigner distribution. So finally, so if I know scattering amplitude, I can immediately think of the scattering cross section. And if I assume that the scattering cross section is scattering cross section is say sigma of E, okay, and this sigma of E, what it represents is the probability of scattering as a function of energy, and it also depends on this what we call as resonance width. So it must depend on it. So what is this sigma is? It is basically f of k whole square. So when calculated, we'll have 4 pi by k square. Then we will have resonance width square by 4 divided by E minus ER whole square plus resonance width square by 4. Now, the cross section that we have here. So we are calculating our cross section in terms of the resonance energy, in terms of the resonance width. And previously we calculated the scattering amplitude in terms of the resonance width. And before that, we concluded our discussion on resonance scattering and obtained a relation between the resonance width and the time. So this equation is called as Bright-Wigner distribution, and the cross section, certainly you can see here, this cross section will peak where will it peak? It will peak at E equal to ER, and this is what we call as FWHM. What does that mean? That's full width at half maxima of this peak. Okay, so what we have done till now, we came up with a resonant state that decays with an exponential law. We saw that the lifetime of the resonance is related with the resonance width that we also did. What was that? Was tau is h bar by resonance width, and then the scattering amplitude and the cross sections we calculated near the resonance, and they are described by Bright-Wigner distribution. So this is our cross section, and we will have a peak when E equals ER, and the width of this resonance width characterizes the energy range. Uh, uh, it gives us a range of resonance and is inversely related to the lifetime of that quasi bound state. So this is where we have reached out in our discussion, and I can say here is that if I have to again, I can say that my wave function, if I write down my wave function, that is psi of x and t as psi resonance of x e to the power of minus resonance width t by 2. So this exponential decay is basically this decay is the characteristic of what we call as resonance scattering. So this is my resonance scattering equation, and it is the solution of Schrodinger's equation in the quasi-bound state which we have already defined. So with this, I tried my level best to obtain some kind of understanding on resonance scattering. With this, I would like to say goodbye and good luck.